Hello, honors physics students. Let's start with problem 22 here. So go ahead and read it. This is why I don't get invited to pool parties anymore. Oh, there's Sadowski with his laser going to show us some physics. Yeah, my friends don't appreciate it very much. Okay, so like we always do, I want you to first draw the pictures. So while we're going to be finding reflected and refracted angles, I want you to first draw the reflected rays on every picture. And then when you're done, you can draw the refracted rays sort of as we go. But let's draw all the reflected rays first. So pause the video, draw all the reflected rays in pictures A, B, and C. Maybe compare to people around you, discuss it, come back to the video. Okay, so I know from experience some students are still a little confused, right? Here's the normal. We draw as a dashed line. Why do we draw as a dashed line? Because it's imaginary. There's nothing there. So we certainly cannot have the light hitting the normal and then bouncing off this way because there's nothing there. It can't bounce off the normal. There's nothing to bounce off of. The light bounces off the boundary. The boundary is the solid line between the water and the air. So in this first picture, light starts by going up and to the right. Which way is the reflected ray point? Down and to the right? It's got to point down and to the right. How do we know the angle? Well, I mean, there's no trick here, right? Theta 1 equals theta 1 prime. Easiest equation all year. Right? So if it comes in at 20 degrees, it's going to leave at 20 degrees. And don't take out a protractor and measure. Just estimate, right? If this looks like about 20 degrees, try to make about the same angle on the other side, right? It's got to be the same. What does the other next one look like? 40 degrees and then 60 degrees. Hey, we've done half the problem already. There's all the reflected angles, right? Again, try to make it look right. It bounces off, equal angles on the other side of the normal. Okay, now it's time to do the refracted part. So go ahead and draw the refracted ray in part A and do the math. Pause the video, come back. Okay, so as we make our predictions, we ask ourselves the same questions over and over. As light goes, in this case, from water into air, is it speeding up or slowing down? And you say, oh, it's going to air, closer to a vacuum, it's speeding up. And you say, does that mean the light is bending towards the normal or away from the normal? You say, oh, speeding up, it's bending away from the normal. So what does that look like? Something like this, right? I don't know how much away from normal, but it's not going in a straight line. A straight line would be 20 degrees, we just keep going. It's going to bend something away from the normal. I don't know how much yet, but you do the math, you do your Snell's law, and you should be getting 27.1 degrees, right? Is that more than 20 degrees? You bet, right? So what comes at 20 degrees, it bends to a slightly larger angle away from the normal, 27.1 degrees. Now, if you made a hugely drastic different angle there, do you want to go back and change it? It's up to you. All right, same deal for letter B. Go ahead and predict what it should do as it comes to the air, then do Snell's law. Okay, so again, we know all that's going to happen is going to bend away from the normal, but here it's got a larger incident angle, so it has to bend more away from 40 degrees. Here's 40 degrees going in a straight line. It's got to bend more than that away. You do Snell's law, make it, you get 58.7 degrees, which agrees with our prediction. Great. Do the same thing for letter C. Draw the picture. Once again, it's got to bend even more away, right? So here's a larger 60-degree angle. We're going in a straight line, but it's got to bend away from normal, so maybe something like this. I don't know how much, but something. You do your Snell's law. And you get theta 2. Uh-oh. Right? You should get an uh-oh. In fact, if you got an answer, you did something wrong. Your calculator should say error, domain error, syntax error. It stops returning your phone calls. It makes a frowny face at you. It starts insulting your mother. So in other words, your calculator is not equipped to do what you're asking it to do. So what are you trying to get your calculator to do that it doesn't want to do? It refuses. Well, you see, you're trying to take the inverse sine of a number larger than 1. You know your trig functions, right? The sine function maxes out at 1. You can't have a number that returns a sine value larger than 1. That's just not how trig works, right? And so there's something physically wrong here. What is happening? Well, let's look at the patterns, right? From A to B to C, theta 1 is getting larger and larger and larger. What's happening to theta 2? Well, it's getting larger and larger as well, right? As you increase theta 1, the refracted angle gets larger. It's got to bend more and more away from the normal. Well, eventually, if you increase theta 1 so much, it's going to refract so much away, it actually doesn't even get out. That's crazy, right? Let's open up our notes, keep the problems in front of you, and let's take some notes on this. This is called total internal reflection. So, let's start by drawing our usual boundary and normal. And we'll set it up like we've been doing. So here's our incident ray. And of course, we know it's going to reflect the same angle on the other side. So whatever that is, just estimate And we can make theta 1 anything we want, right? We can direct the light ray at any angle we want whatsoever. We're going to do it so that it bends so much away from the normal, it goes actually along the surface. So when this happens, theta 1 is a special angle called theta sub c for critical angle. Theta 1 can be absolutely anything, right? You can have this ray go here, 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 anything. But at one particular angle, theta critical, the refracted ray bends away from the normal 90 degrees. Makes a right angle with the normal. So theta 2 is 90 degrees. It's actually along the surface. Let's now develop an equation for this critical angle. We start with Snell's law. Remember, theta 1 can be anything, but at this particular angle, we rename theta 1 as theta critical, and at this particular angle, theta 2 is 90 degrees. So we'll replace both of those in this equation. Theta 1 becomes theta critical, theta 2 becomes 90. What's sine 90? You all know, of course, is 1. So it goes away, we rearrange, and solve for theta critical. I know I sort of gave the answer away there, but make sure you can do those steps and get to this. Don't just take my word for it. Make sure you know how to solve for theta critical. I'll box this in. Let's define our term here. Theta sub c is this critical angle. It's one particular angle where this idea of total internal reflection first happens. Remember, theta 1 can be absolutely anything. So what are the possibilities? Well, if theta 1 is less than theta critical, the light escapes. Everything happens like normal. Nothing weird. If instead theta 1 is larger than theta critical, well, that's when the light gets trapped. It gets totally internally reflected. It doesn't get out. P.S. little side note. I always felt if you were going to go to a battle of the bands with a physics-themed emo band, total internal reflection, I think, would be a really good name for that band, right? Think that went through. That's a good one. Yeah. All right. Anyway, so it's all about how it relates to theta critical. Theta critical is sort of this dividing line where the light can escape out into the new medium or it gets trapped inside. What happens when theta 1 actually equals theta critical? Well, the physicists themselves actually can't agree because here's what happens. The light goes along the boundary. And so some will say, well, it refracts because it changed direction. Others will say, well, it doesn't get into the new medium, so it doesn't transmit into it, so it doesn't escape, so it doesn't refract in that way. And so don't worry about it. We're not going to deal with what happens when it's at theta critical. It's just these conditions here, whether it's less than or greater than theta critical. Let's make sure we understand the terms here, N2 and N1. N1 is the first medium, so that's the medium that traps the light. N2, that's the second medium. That's where the light tries to go. You're directing the light at that second medium, but it never gets there if theta 1 is larger than theta critical. It gets trapped inside. Now you say to yourself, this can't possibly happen, right? There's no way light can actually get trapped. Well, here's a photograph of it happening. So here we have some medium and an air above it, and different sources of light angled different ways to that boundary. Here the light gets out and reflects. Gets out and reflects. And here, when it comes in at such a large angle to the normal, it doesn't get out. It's trapped inside. Now notice this reflected ray is much brighter than the reflected ray over here. Why would that be? Oh, because here, light splits up. Some gets out, some reflects. Some gets out, some reflects. Here, it gets totally internally reflected. None of it gets out. All light gets reflected back in, so it's a lot brighter. All right, so now what I want you to do is go on to problem 23, find the critical angle for water. Use our new equation. When it says just find the critical angle, you're assuming the other medium is air. So this is basically referring to problem 22, when light starts in water and is trying to go into air. Anytime it just says find the critical angle for a particular medium, assume the second medium is air. They'd have to go out of their way to tell you that the medium you're looking at is surrounded by something else. Okay, so you should be getting 48.8 degrees for the critical angle for water. What does that mean? Well, let's go back to problem 22 and see what happens, right? So in the first example, theta 1 was 20 degrees. Well, that's less than 48.8 degrees, no problem. The light gets out. Some of it gets reflected, some of it escapes. And letter B, 40 degrees. That's still less than 48.8. Some gets out, and some gets reflected. But 60 degrees, that's the problem. Here, theta 1 is larger than that critical angle, larger than 48.8 degrees. So all light gets reflected in. We really need to get rid of that. None of the light gets out because theta 1 is larger than theta critical.